Hey everyone, I'm Gil, an instructor at Treehouse, where you can learn the in-demand technology skills needed to land your dream job. We offer thousands of videos created by expert teachers on coding, designing, and much more. If you'd like us to publish more free, high-quality courses like this, please like and subscribe. Check the description for a link to download and work with all the project files used in this course. Happy learning!
Hi, I'm Craig, and I'm a developer. In this course, we're going to be taking a look at Python's wonderful data library, NumPy. You'll find NumPy in all sorts of applications, and therefore, it's fairly critical that you have an understanding of its fundamentals. It appears in every direction you may head in Python. Should you plan to get into data analysis, or scientific computing, or even machine learning, you're gonna bump into NumPy. And that's what this course is all about. It's an introduction. I want to introduce you to the library early on. We'll walk through hands-on examples that will give you a great introduction to the library, its main concepts, and the surrounding terminology. When you've completed the course, you'll have a great foundation and you'll know where to turn when you need more specific information. But before we get started, let's take some time to make sure that you're familiar with your learning environment. First off, there are some prerequisites to this course, and I'd love for you to make sure that we're on the same page about where you are in your coding journey. There's speed controls on the video player, so please feel free to speed me up or slow me down. Pause me, make me repeat myself, whatever you like. I won't mind at all. You are in complete control of your learning. A quick reminder, there are notes attached to each video. This section is usually filled with additional information that will enhance your knowledge should you want to dive deeper into related topics. Get in a habit of checking this space, and I'll do my best to remind you when I've put info there that you just have to see. One more tip. Remember that there is a community of fellow learners also taking this course. I encourage you to lean on each other. If you have a question, make sure to ask it. Our community is very friendly and approachable. Also, remember, nothing helps to cement your learning better than answering a question. Make sure to check out the community throughout the course and see if you can help out a fellow learner. We've established that NumPy is extremely popular in many fields of the Python landscape. But what is it exactly? Now, NumPy is short for Numerical Python. It deals with numbers. So that makes sense. All those applications that I mentioned would indeed need to use numbers and math equations in some shape or form. But as someone who is actively learning Python, you might cleverly state, wait a second, I can use numbers and do math just fine in plain old Python. What's the big deal? Why do we need this? That's a wonderful question. And the short answer is that NumPy is much faster than the straight Python approach, no matter how great of a coder you are. It leans on a paradigm, which we'll get into here shortly, called array programming. It completely removes the need to loop over your data, which speeds things up tremendously. NumPy also provides additional mathematical abilities not available in standard Python. Many numerical concepts have been abstracted away for you and provided as functions. And chances are, you probably aren't going to use all of those helper functions. However, the applications that you're building, the ones that are relying on the library, they most likely will. NumPy exposes concepts from linear algebra, matrix multiplication, Fourier transformations, and many more themes that you might remember from your math class, if math isn't your area of study. Now, just a heads up, it's totally fine if math isn't your jam. It really doesn't need to be. That's kind of the beauty of these abstractions. You'll use them when you need them. My advice is just to stay focused on where we're headed and don't let the shiny tools and terms distract you too much. I'll point out what I think is important at this part of your learning journey. Now, believe it or not, that was the short answer to the why would you want to use NumPy question. The long answer is going to take me a couple of videos to get you to see the beauty that is NumPy. One of the more challenging tasks of picking up NumPy is simply just remembering how to use the objects that it provides. So I was thinking of facing that challenge head on. Let's do this. Let's build a Jupyter notebook together, and then you'd have a reference, and we could kind of treat it like a cheat sheet. You could then quickly glance at it or even practice some more with the datasets that we build up. Sound good? Speaking of practice, that gives me a great idea. Have you heard of the movement called 100 Days of Code? It's a wonderful idea that a lifelong learner, Alexander Calloway, came up with. The way it works is this. You publicly commit to coding at least an hour a day for 100 days. You post about it on social media, usually Twitter, and you hold yourself accountable. It's wonderful for learning. Steady practice will strengthen your skills. It creates a great habit of learning. It also seems like a great way to explore the NumPy array data structure. We can use it to track and analyze our time. The only downside I can see is that it might create some pretty meta tweets. If you are committing to learning NumPy and creating a log to help track and analyze your 100 days of code in NumPy, reporting on your learning is going to create a tongue twister of a tweet. You'll figure it out. So what are we waiting for? What do you say we get things all set up? There are a couple of ways to get things installed here, but by far, the best way to experiment with a package, in my opinion, is by using Anaconda. If you haven't heard of Anaconda, it's a distribution of all the popular Python data libraries. I'm actually going to use a smaller version of it called Miniconda, but either will do. We offer content on how to get it installed if you don't have it already. It's in the teacher's notes. If you don't have Miniconda or Anaconda installed, why don't you pause me and get that installed and then come follow along. Let's get things cooking. So here I am at my command prompt, and I'm going to make sure that I have conda installed. So I'll type conda -- version. Awesome, I do. Okay, now I'll create a directory called intro to NumPy. And I'm going to change to that directory. So cd intro to NumPy. And now I'll make sure that I create a new environment. So I'm going to say conda create. And I'm going to name it 100 days. And then what we want to install is NumPy and Jupyter. You just kind of list them off here, the things that you want. So we definitely want NumPy and Jupyter. And this will kick off and set everything up for us. And Conda saves environments to make sure that things are always at the right version by providing a virtual environment. So I'm going to let this go. It's going to take a little bit. See you when it's done. And there we go. Everything's all installed. Awesome. So I'll activate our new environment. So we'll say conda activate 100 days. Oh, and I got a big error message here. Let's go ahead and I'm going to grab this here, this echo. We're going to echo into our profile.d file here on Mac. Let's paste that here. So now that I pasted that into the profile D, I need to restart my bash. So I can say bash profile. And now I should be able to say conda activate 100 days. Awesome. And now I can open up our Jupyter server. So I'll say Jupyter notebook. And that popped open a brand new window, which I'll bring over here to us. And I'm going to choose over here this new. We'll do new Python 3 notebook. And I'm going to come up here and I'm going to rename this to Introduction to NumPy. Okay, and I want this first cell here. I'm going to make this first cell Markdown. And I'm going to write heading 1 of Introduction to NumPy. And we'll just say Learning NumPy. So I'd like to repeat that I'd love for you to follow along and make your own notebook. I'll give you mine when the course is over, so you can have all of my notes. But please, feel free to make your own comments. I find that when using these notebooks, it helps to capture your thoughts to review later. I really like using these for cheat sheets. So we can actually run this cell and enter the next one by choosing Option Enter on a Mac. So Option Enter. And just a quick heads up, I love keyboard shortcuts. You can pick up some great productivity by learning them. So open the list here and kind of type what it was that you were looking to do. So we were looking to run that cell. So if I type run, and we'll see here we have run cell and insert below. That's what I did. So this is Option Enter. This will look different if you're running this on Windows. Pretty cool, right? Okay, so the new cell that was created here is Python by default, right? So it's code. I want to make sure that we got things installed correctly. So what I'm going to do is I'm going to import NumPy. Now, as it turns out, data scientists are just as lazy as programmers and don't like typing more than we need to. So a very common way to use NumPy is to import it as MP. So you say import NumPy as MP. And that will allow you to skip some unnecessary characters. We don't want to type more than we need to. Where, of course, that stands for NumPy, but I like to think of it as no problem. And that's because when we're done here, NumPy will be no problem. Like most great libraries, the NumPy module exposes its dunder version. So we'll just write that here. Let's put that in the same cell here. We'll say np.under_version. And remember, in Jupyter Notebooks, when you run a cell, the last line, it will show its output. So here we go. And you'll see that I'm running version 1.14.5. Now, you are most likely using a more current version than I am, and there shouldn't be any breaking changes for this course between your version and mine. But that said, I can't predict the future yet. So, therefore, if there are any problems, I'll make sure to list those in the teacher's notes. So please, take a moment right now to check those out. I don't want you to have any problems. I want you to have no problem, NP, with NumPy, NP. All right. Now that we have our environment all set up correctly, let's dive into learning the most critical data structure of NumPy, the array. Arguably, one of the most important things to get familiar with in NumPy is the array data structure that it introduces. Arrays are around in most programming languages, so you've probably heard the term floating around before. Now, don't worry if you haven't. You'll be super familiar with the concept here shortly. Python actually has an implementation in its standard library. Arrays are a way of organizing your data. An array is a data structure that allows you to store multiple items in a single variable, which, yes, wise Pythonista, sounds an awful lot like a list, doesn't it? But there are some crucial differences between a list and an array. The array is much more restrictive than a list, which I realize doesn't sound like a great selling point. But in fact, it's actually these restrictions that make arrays the go-to solution for most Python projects involving data. A list, as you know, can contain just about anything. And by anything, I mean the type of elements in there don't matter, right? A single list can contain Booleans and strings and any random old object. Arrays aren't like that. Every single item in the array must be of the same data type. That's the first major difference between the list and an array. Now, the second one is that the array's length cannot be changed. Its size is immutable. You can't add items to the array or remove from it. You can change the value of individual items, but the size cannot be changed. And it must be defined when it's created. When we work in these higher level languages, like Python, we don't really need to think about how things are working under the covers. That's because the language does a wonderful job of abstracting that away from us, right? What do you say we take a peek behind the curtain real quick? When I create a new variable named age and set it to say 29, I wish, what really has been abstracted away is that Python has to go to the memory on the computer and find some free space to store that number. And storing that number is actually another abstraction, isn't it? It's really just binary, right? It's a series of ones and zeros that gets put in there. And then later, when we go to access it again, our variable name references that memory location so it can be used to go to and read that value from memory. And because it knows the size required for its data type, it can grab the right version of ones and zeros to have it represent the original value in our program, 29. I feel like I have aged a year just explaining that. There are lower level languages like C where you actually have to do all the memory management. You have to go find the space yourself, put the value in there, and clean it up when you don't need it anymore. Now, I'm certain that you could totally do that if you had to, but this work has been abstracted away from you, so you can focus on more important things. One thing you probably don't think about often is how awesome these Python lists actually are. You create them, you append stuff to them, you remove stuff, you insert stuff. That stuff can be any size, so every time something is added, the same flow of finding the proper space with enough room to hold that data needs to be located. And there's even more to the list abstraction here. Each of those whatever size objects all can be iterated through or accessed by index. It's pretty impressive when you stop to think about what we've been taking for granted. There's a lot of effort that is hidden behind that abstraction to make things seamless. That effort actually does have a cost, namely speed. It's a lot of overhead, and it wouldn't be needed if only you knew how much space each element required, as well as the total number of elements that would always remain the same. Hey, those restrictions sound pretty familiar, don't they? Those are the restrictions I was talking about that arrays have. When the array is defined or declared, the only type of element that it can store is defined, as well as how many elements will ever exist. Therefore, the space to store the whole array structure is known at creation time. What this does is it allows for each element to be stored next to the following one. The elements are contiguous, or one right after the other, with no space in between them. This makes finding exactly where an item lives in memory a very easy math equation, much quicker than accessing an item in a list. Let's go build an array.
Okay, I'm going to give us a little more space. I'm going to click View, and I'm going to toggle the header. That feels better. Let's start by building a list that we can use for a quick refresher. So I want to store some floating point numbers. Okay. Well, how about we store my high school GPA scores? For those of you out there outside of where I grew up, which is the United States, GPA stands for Grade Point Average. And we are, or at least at the time, a little over-obsessed with them. Now, it's an average of all your grades in all subjects on a scale from 1 being the lowest to 4 being the highest. Okay, so let's declare a new list called GPAs as list. And we'll use a hard bracket literal for our list. I'm doing this for high school. Now, this is the part of school before college. It's called secondary school elsewhere. Okay, so what did I earn? I don't remember really. I've forgotten it because I didn't really use these things. So our brains tend to forget information that we don't use by design. Well, I know I started off strong. So I'm going to give myself let's give me a 4.0. And then let's see, math started to get a little weird. Remember geometry and whatnot. Oh man, and chemistry. I must have dropped a bit. Let's do 3.2. Well, shucks, I'll give myself some more precision there. So let's do 3.286. It's better. And then we had some trigonometry. It was still pretty rough, but I started building out that math foundation. So let's say 3.5. And then let's not even talk about senior year's physics and calculus. Okay, fine, I'll add it. And I can because a list size can be mutated, right? So I can just append to it. Let's say 4.0. I did have a hard time that year with calculus, but eventually it all started making sense once I got that graphing calculator working. And I haven't thought about that sweet TI-82 since then. I'm going to make a little note here about this list too. So we'll put a comment in here and we'll say can have elements appended to it. So on top of appending, I can also insert into the list wherever I want. So, and also we can have multiple data types in this list, right? So let's do GPAs as list dot insert because we can put them anywhere. And at the first position, we're going to insert whatevs because that's a string in there. So that's kind of strange. And I can pop it right out, right? So I can say can't have items removed. So we can say GPAs as list dot pop 1. And I'm going to run this, and we'll see that we got back this last line here, this pop. Whatevs is right. So we can stick whatever in there. So let's take a look, make sure we got everything looking like we want. Awesome. Now, let's create a NumPy array. A common way to create an array is to pass the array function an iterable. And we have one of those. So let's go ahead, we'll make a brand new array, and we are going to call it GPAs equals numpy.array GPAs as list. So now that we have one, let's see what we can do with it. One of my favorite things about Jupyter Notebooks is that it lets you peep the documentation on an object. If I just say $GPAs, nice. So this is an ND array. Some documentation here. Here's some parameters. Here's D type, the data type, and here's some attributes for it. So D type, the D type describes the format of the elements in the array. Awesome. So let's just go ahead and see what we have going on here. So if we say GPAs.dtype, float 64. 64 there stands for the number of bits. Remember, the ones and zeros that are required to store the data type. Oh, speaking of which, looks like we also have item size, the memory use of each array element in bytes. So we can say GPAs.item size. 8 bytes. That makes sense, right? 8 bits are in 1 byte, And our data type, 64, takes 64 bits. So 8 bytes is 64 bits. 8 times 8. All right, so what else do we have in here? Size. That's a great one. So let's take a look. So we have GPAs.size 4. And NumPy does a pretty good job of being Pythonic, which means most objects just work like you think they should. Like, if I wanted to know the length, I should just be able to use the len function, right? So we could say len of GPAs. And while not the best naming, we can also get the number of bytes that are required for the data. So if I say gpas.inbytes, we'll see 32, which of course is just the length, 4, times the item size, which is 8. So 32, but it's still nice to have. Okay. Whew. I just threw a ton of information at you. So let's go ahead and take a quick breather. But before we do that, let's do this. Let's do a little exercise of writing up a nice summary. Try to capture our train of thought. We found that reflecting on what you just learned will help you when you come back to it later. I'm going to come up here. So I'm going to get in command mode by pressing escape. See how it's blue? I'm going to come up here and I'm going to go right above this GPAs list here. And I'm going to make a new cell. So I'm going to make a new cell above this. So A, I'm going to press the A key. There's a new cell above it. I'm going to press Enter. And I'm going to switch this to Markdown. And I'm going to write down some notes here. So I'll say pound for second heading. We'll say differences between lists and NumPy arrays. And during the break, I'm going to do some reflection. And I'll share with you what I jotted down in the next video. But I'd like for you to give that a shot too. Treat it free form. Just jot down some thoughts. And like I said, I'll share mine with you in the next video. Sound good? Okay, so do that. And when we come back, we'll start our 100 Days of Code study log. So how'd you do with your reflection? Now, here's what I came up with. So my first point is an array's size is immutable. You can't change it, right? So you can't append, insert, or remove elements like you can with a list. And we showed that down here. All of an array's element must be of the same data type. I went and did a search for the different data types that are available, and I made a little link here. I like to use those as bookmarks, and we'll actually use this one here just in a bit. And then finally, a NumPy array behaves in a Pythonic fashion. You can use len myArray just like you'd assume. Awesome. How'd you do? That feel good? All right, are you ready? Let's build out our study log. We should track how many minutes we studied for each day. Now we know that there are exactly 100 days in the challenge. And since we can't add or remove entries, we know that the array that we create will need to be 100 elements. Now, before, when we created our array, we did it from an iterable, right? Remember, we did this NP array and we passed in this list here. But in this case, we don't have an iterable. We don't really have any data. But we do know that we eventually will. This is a common enough problem that there is a provided solution. What we want basically is a 100-element array where each element will represent the minutes that we coded each day. And we want each of those elements to be initialized with the value of 0. Lucky for us, there's a helper method called zeros that does just that. So let's do it. Let's create a new array called study minutes. And it's right off of that package. So mp.zeros. And the first parameter is the shape or size. So we want 100. Awesome. And if we look at our study minutes array, we could do that just by putting it right underneath here. We'll say study minutes. And there we go. 100 elements, 100 zeros. And you'll see that these zeros have this dot here. And that's showing that these are floating point numbers. Now, one thing that we can do with the Jupyter Notebook is to get some additional information. And we can do that using the whos command, H-O-S, this magic command, whos. If we do that, we can find the study minutes array, and we can see that it's 100 elements, and it's of type float 64. That must be what the default is happening, right? So it takes 64 bits, or 8 bytes, to store each of those. But we know something about these values, don't we? We know that there are 60 minutes in an hour and that there are 24 hours in a day. And therefore, we know that the max value could only be 1440, which really isn't too large of a number. Let's go ahead and use that link from before and see what other data types are available. So let's come back up to these notes. I'm going to go ahead and click this. Okay, so these are the different ranges of values that things have, and we're at float 64 right now. So double precision float, there's a sign bit. We don't need all of that. It's a lot of precision. We just need minutes up to 1440, not portions of a minute. So we don't need a floating point at all. So we're probably up in this integer area up here, right? So integers, right? Those are whole numbers. And in fact, you can't study negative minutes in a day. So we need an unsigned integer. That will be always positive. See, these go negative. We only need 0 forward, right? And so we need 1440. So this first one, this uint, that's again unsigned integer of 8 bits. We can probably get it here, right? Because this 1440 is in between here. So we can use this uint 16. So the data types are available as np dot the name of the thing afterwards. So we can use that. So let's flip back to our example. We're down here at our study minutes. And let's go ahead and we can put in our data type is np dot uint 16. And now remember, this was at 800 bytes. So it took 800 bytes before. So let's go ahead and let's specify the data type. I'm going to go ahead and run this one more time. And you'll see the dots are now gone. Now if I rerun this whois with control enter, you'll see that it's now 200 bytes. Now at this time, what we did is probably a little bit of premature optimization. We only have 100 entries. But I want you to imagine these arrays as enormously large. They tend to get that way as you work with larger and larger data sets. Constraining to the proper type can save a lot of space and, in turn, speed by specifying a data type to meet your needs. I've started this challenge already, and on the first day, I plugged 2.5 hours into it. Now, you only need to do 1 hour each day, but I was super into the challenge, and I hope you will be too. So 2.5 hours is 60 plus 60, 120 plus 30, 150. Okay, so I'm going to set my minutes for the first day. So an array element can be set by its index, just like lists. And just like lists, the indices are 0-based, right? Remember, the first element is 0, the second is 1, and so on. So let's do that. Let's set this. We'll say study minutes 0. And we'll set that to our 150. And you can retrieve the value also by using the index. So we'll say first day minutes equals study minutes 0. And if we take a look at first day minutes, see that 150 came back. That's interesting though, isn't it? We know that when we put our value of 150, when we put this in here, we know that it got coerced or transformed into an unsigned integer 16, right? So we know this is a uint 16, but this looks like it's just 150. Why don't we take a deeper look at this? So let's say type of first day minutes, and we'll see what comes back. Nice. It's just cleverly wrapped in what is known as a scalar data type. Here you see that the scalar data type is uint16, which is what we declared each of the elements to be. Scalar is a term that comes from mathematics, and for our purposes right now, it can be thought of as representing a singular value. Now, you'll hear the term scalar thrown around for values that are a single element, and the term vector for those that are multiple. You'll also hear arrays and vectors used interchangeably. Now, this naming comes from their common mathematical use cases, which we're going to touch on here in a bit. For now, though, I want you to just know that the single values pulled out of a NumPy array are scalar and wrapped in their specific data type object. These scalar objects provide the same API as arrays. This is so that scalar objects can interact with other arrays easily. Again, don't fret too much about this. We'll get into it as the course progresses, but check the teacher's notes for more information on scalars if you're interested. Let's go ahead and fill in the second day of the challenge. I was able to sneak in some code after I got my kids to bed. I've been working on this microcontroller project, and I was able to get some progress on it. And the challenge encouraged me to do it. So I spent about an hour on it. Okay, so how would I track that? How would I go about doing that? So I want to put 60 minutes into the second day of the challenge. Hey, how about you give that a shot? Just to make sure the stuff is sinking in. So I'll do a to-do here, and you do it. So to-do, add 60 minutes to the second day in the study minutes array. Pause me and give it a go. And then after you get it, unpause me, and I'll show you how I did it. Are you ready? Pause me. Okay, so I can't tell you how many times this bites me. I said second day, so I feel like it should be index 2. But it isn't, is it? It's actually index 1. And I'm going to set that to 60. Now, you might be wondering if you can assign multiple values to an array in a single line, in a single statement. If you remember your collection slicing skills, they work here too. So I've got 4 more days of data to enter. I kept plugging away, and let's see, I had 80 minutes and on day 3, and then I squeezed in another hour of 60, and I only got a half hour on day 5, so it doesn't actually meet the challenge criteria of doing an hour a day. But you are allowed 1 day of wiggle room, so I didn't break the challenge. So I kept going, and I made up for it, and I got 90 here. So I want to add these into the study minutes array. And I want to start at the 3rd day. So we'll say study minutes. I'm going to start at the 3rd day. So again, that's 2. There are 4 of them. So I want to go up to the 6th day. So the way that slices work, remember, is they are exclusive. It does not include that 7. So we're going to say 2 to the 6th. So that's not the 7th day. There we go. And that should do it. That will set it. And then if we go ahead and take a look at it afterwards, we say study minutes. Give that a run. We will see, boom, there they are. So we got 150 on our first day, 60 on the second, and here's the values, 80, 60, 30, 90. Awesome. If your slicing muscles are out of shape, don't worry. We'll exercise them throughout this course, and you'll be super fit when we're done. Well, one thing we didn't go over earlier when we ran this Jupyter Notebook whos command is that you'll notice the data type here is ND array. Now this ND, it stands for n-dimensional, meaning the array can have many dimensions, which is to say that these arrays can be multi-dimensional, which I realize sounds a lot like a science fiction term. We'll get to what that means exactly right after a quick break. Hey, during that break, why don't you do a little reflection, specifically surrounding what we went over about data types and choosing the right one and how it can save space. I'm going to put my notes in here right above this call, right above this call to 0. So I'm going to press escape. I'm going to get back into command mode. I'm going to press above. Then I'm going to get this into Markdown. There's probably a keyboard shortcut for that. Share about that. So I'm going to say about data types. And again, just like before, I'll share mine right after the break. Take some notes about what we learned here. See you soon.
Multidimensional is such an intimidating sounding word, isn't it? It sounds futuristic and outer spacey. I mean, what does many dimensions even mean, especially in the context of an array? Well, the answer is kind of boring in comparison to how cool it sounds. If you think about what we've been doing so far with our arrays, we've basically been building a container where each slot represents something. For instance, in the grade point average example, each element represented a single year of school. So we could say that this is the year dimension. Now let's imagine that we wanted to track every student in my graduating class. Now, of course, we could add a separate variable for each student, but wouldn't it be nice to store that all in the same variable? Well, you can. What you do is you add a new dimension, the student dimension. Now, we essentially have rows, where each row represents a student, and each column here represents a year. And would you look at this? We have 2 dimensions. And really, a 2-dimensional array is just an array of arrays, right? I can access the student I want, like the 3rd one here, and then I could select which year I want. I want the sophomore or 2nd year. There's a term that is used to discuss how many dimensions an array has. This is called rank. So this GPA example is currently rank 2. Now, fun fact about two-dimensional arrays, you remember how single-dimension arrays are often referred to as a vector? Well, a two-dimensional array is referred to as a matrix. Whoa. Now, remember these are called ND arrays. And again, the N represents any number because you can have as many dimensions and ranks as your heart desires. Like we could add another dimension of school, where each school had all of their students. So that's 3D. And most likely you'll need to wear these glasses to see that. Sorry, that was a bad joke. But see, now we have an array. I'll choose the first element, and that is our array that contains arrays. All right, not as intimidating as it sounds, but I bet you feel like you need some practice to fully grok it, right? Let's do it.
So first, let's review our notes. So here's mine about data type. So by choosing the proper data type, you can greatly reduce the size required to store objects. Remember, we saw that. And again, I put the link here just to jump off to that data type page whenever we need it to review later. I think that's handy, bookmarks, sort of. Data types are maintained by wrapping values in scalar representation. Remember when we pulled that value out of the array, it still knew the size that it was, even though it kind of looked like it didn't. And it was a singular value, which is scalar. NP zeros is a handy way to create an empty array filled with zeros, like we did right here. So we did this and we pushed the data type of the U unsigned integer 16. Awesome. Okay, so let's return to our GPA example, which is here. I'm going to click in here, put it in command mode, and add one below, so B. And what I'd like to see here is a new array. We will make students GPAs. So it's a list of students' GPAs, and we'll make a multidimensional array. So we'll say np.array, and we're going to pass in an iterable again. And we are going to make this iterable just be a list of lists. So first we'll push mine through here. So we had this. I copy that and paste this here. And I'm going to do a comma, and I'm going to add another list. So let's add another student. Her name is Vlada. She struggled at first. English was not her first language, but then she totally nailed it. So she had a 3.2 her first year, and then she started getting a lot better, 3.8, and then by the end was just sailing, 4.0, 4.0. Awesome. And let's see, one more. Let's add Kwesi. He was on fire all through school. He started with a 3.96. He got a 3.92 his sophomore year. Then he ended out with 4.0s and 4.0, 4.0. Awesome. So let's make sure that we grab the right data type for this. So right now, the second parameter we've been leaving empty. Let's say np dot, and then what do you think that was? Let's see. Let's use this link one more time. We'll click this. Oh, I already have it open here in a tab. So this data type, let's say it's at float 64. We definitely don't need that. We should be totally fine with just this float 16. So let's use float 16. So we will build our student GPA with a float 16. And then let's take a look at it too. We'll say students GPAs. So this is really just an iterable. It's a list of lists. So each element of that list is another list. Okay, list of lists, multidimensional list. So let's go ahead and take a look at it. Awesome, and it looks exactly like we want. It's an array of float 16, and it has all of the values there. Now, it's possible that we would have run into a bit of a precision error, but we didn't. We haven't run into that here. But just in case, because we did set a data type, it might change the precision. Check the teacher's notes for more information on that. So we now have a two-dimensional array, right? We have rows, and we also have columns, right? We have these columns here. You can always look at the property on an array to see how many are there, and we have .ndim for number of dimensions. See that it has 2. If we wanted to see how many elements are in each dimension, we can actually view that. That is exposed using what is known as shape. So we can say students under GPAs.shape. This is saying 3 by 4, and there are 3 rows and 4 columns. Each element in this tuple represents the length of each axis. So that's another term that you'll see used to describe dimensions. The plural for axis is axes, not like what Paul Bunyan had a bunch of. He had axes. These are axes, A-X-E-S. So in our case, the first axis is students, and the second axis is years. Axes are zero-based, so axis 0 is 3, and axis 1 is 4. Now, one thing that might bite you if you aren't careful is that if you use the size property, so if we say students GPAs.size, it's going to tell you all of them, not just the first dimension. If you want to see just the first dimension, you can still use len, and that will just show you how many students there are. 3. There's also a property that we can peek at called item size. So again, students GPAs.item size. And that shows you how many bytes are being used for each item, which means now we could calculate how much space we're taking up if we did students GPAs.item size times students GPAs.size. We're taking up 24 bytes, which lines up with exactly what you would see if you were to use the whos command. So say whos, and then if you follow a type nd array, it'll show us all the nd arrays. So here's the 4x4. This is the singular one that we had. And look, that was 32 bytes. And here's 3x4, and it's 24 bytes. It's already smaller. Data type savings for the win, right? This whos is a Jupyter Notebook special command, but you could also grab this information and any information of a NumPy object using a function named info, np.info, and we can pass in students' GPAs. And if we take a look, we can see there's the shape, 3.4, there's our item size, and here's the type and some more information. All right, so let's access some things. So if I wanted to get access to the third student's record, I could just do this. I could say students GPAs 2. And that is the third student, right? That's Quasey's grades. And see how that returns me an array? So of course, if I wanted to, I could just chain off of it, right? Because it is an array. Like, let's say I wanted to get the last year here. So I could just get this last year, this last 4 here. So I could say students GPAs 2. So that will get us the student there. And then I just get 3, and it should return back 4. Awesome. This is just one way of accessing this value in the 2-dimensional space. And remember, this 2D or 2-dimensional example is synonymous with the term matrix. Whoa.
Sorry for making multidimensionality seem a little less futuristic than you probably anticipated. It still sounds cool though, right? So make sure you drop it when someone asks what you're learning. Oh, just coding in a couple dimensions. I do hope it's pretty straightforward, and we'll get lots of practice working in dimensions through the rest of this course. Now that you've got a handle on the main data type and most of its terminology, let's go ahead and wrap up this first stage. We'll go deeper in the remainder of this course, and I'll show off some great shortcuts, as well as how to use these powerful multidimensional arrays to your advantage. For now, though, why don't you make sure you reflect a bit on multidimensional arrays and add some thoughts to your notebook. And please remember to take a break and let all your learning sink in. You deserve it. See you in a bit. Welp, it happened to me. I had committed to code an hour every day for the 100-day code challenge, and sure enough, I didn't make it. I missed 2 days in a row, thanks to a Netflix binge. We've all been there. And sure enough, though, technically, I broke my commitment. I was pretty bummed about it. I was really enjoying the challenge. Now, the good news is you can start your challenge over without losing your previous wins. What you do is you just start a new round. Whew. Now, if you've started the challenge, you might have seen people using that syntax in their tweet, R1D6, which stands for round 1, day 6. But that brings up an interesting point. How would we represent that in our study log array? Currently, each of our columns is used to represent a day. Remember, it's a 100 element long array filled with zeros. So how could we also track rounds? You know what, you're right. We just need a new dimension, don't we? Good thinking. Come help me out with this so I can get back to studying.
Before we get to upgrading our study log, I'm going to review my reflections of multidimensional arrays. I feel like I forgot a bunch of the stuff while I was binging that Netflix series. A good thing I wrote it all down for my own recall. So the data structure is actually called an ND array, representing any number of dimensions. That's where the ND comes from. Right, and arrays can have multiple dimensions, and you declare them when you create them. Cool. Dimensions help define what each element in the array represents. So a two-dimensional array is just an array of arrays, like multidimensional lists. Rank defines how many dimensions an array contains, and shape defines the length of each of the array's dimensions. Remember, that was like 3, 4 that we saw, right? And each dimension is also referred to as an axis, and they are 0 indexed. Multiples are called axes, even though it looks like Paul Bunyan's axis. And a two-dimensional array is also known as a matrix. Awesome. I am refreshed and ready to go. Now, there's a couple of ways to add a new dimension. Let's explore one of them. Let's get back down to where our study log is. Here we go. Here's our study minutes array. Go ahead and get rid of this where we print it out one more time. And run that one more time. There we go. So let's make a brand new array, which consists of our array and a new row of zeros. So we could do that pretty easily. We'll reassign, we'll relabel, we'll remove the study minutes label from the other one and put it on this new one. We'll say np.array. And remember, arrays accept iterables, and our study minutes is iterable. So we'll say study minutes here. So that's an array of an array. So we'll just do np zeros 100, and we'll do np.uint 16 because that's what the original value was there. And let's go ahead and run it. That seems like it worked. Let's go ahead. Let's check the shape of that. So we'll say study minutes does shape. Awesome. 2 by 100. So our first axis, 2, will represent the round, and our second axis will recommend the day. So this 100 here, right? So this is axis 0 and axis 1. We have 2 dimensions, and our array is now of rank 2. So I did, in fact, complete an hour on that first day of round 2. So that's R2, D1. Do you remember how to access that element? Why don't you go ahead and do that? Why don't you set round 2, day 1 to 60. So pause me and give it a go. When you're ready, unpause me. Ready? Now, remember, it's 0 base. I hope you didn't fall for that. I hate trick questions. So that's study minutes. And we want to get the second round. So 1. And then we want the first day. So that's 0. And it was 60 that we're going to set that to. And then let's go ahead and let's peep it. Let's see what we got going on here. Awesome. So this is the first round, right? The first round goes all the way there. And then here's the second round. There's the 60 that we got in there. Great. We did it. And we'll come back up. I'm going to get rid of this displaying of it. And we will run that one more time. Get our space back. So you did it. Great. But this syntax, all these brackets, it's kind of clunky, isn't it? Well, NumPy introduces a fun shortcut of a comma. So if we wanted to get the value from here, we could just say study minutes, and we could say 1, 0, which is the second row and the first column. Let's see if that works. And it does. It feels better, right? And it's kind of cute. Now, what's happening here, it's a little subtle. It might look like magic, especially if you haven't seen this before. But if you separate values with a comma, like we did here just in plain old Python, check it out, a tuple is assumed. So really, this is just a tuple in here, but we don't want to add all of these parens. We don't need them. So it looks nicer like this. It's easier to read. So in this case, each of these values represents an index to each of the axes. But there's another way that these indices can work. And I want to bring this up now because it can be a bit confusing if it catches you off guard. There's a bunch of stuff that happens within these hard brackets, and we haven't even got to slicing yet. It's going to sound like I'm making this up, but I want to talk to you about a special type of indexing called fancy indexing. In order to show this off, I'd like to start with an array that is a single dimension. And since our example arrays are now both two-dimensional, I thought I'd show off a handy tool for creating some random data to explore. Let's do this. Let's make a new study log, but instead of just zeros, let's make it contain fake but reasonable data. Now, this random trick is a great way to create data to play with. So here we go. So you can actually create a random number generator and seed it in a way that will always produce the same results. That way, we can have the same random data, you and me. The seed value, so let's do this. So it's np.random, and we're going to create a thing called random state, and we'll pass it a seed value. And the seed value I'll use, let's use 42, the answer to life, the universe, and everything. And now let's make a new fake log. We'll make a round that was just totally fake, and we'll use random integers. So we'll say fake log equals rand.randint, because we want an integer. And we'll make the first parameter, it's the low value, like how low should it ever go? We want it between 30 and then the high of 180. That's 3 hours. That's tons of studying. And then we'll set the size to be 100. We'll say size equals 100. And we'll set the data type, or D type, to the same thing that we've been using, uint16, the unsigned integer. Let's go ahead and do that, and then let's peep it. We'll do fake log. There we go. This is nice. Aren't you glad we didn't have to type out all of these values? Aren't you glad we didn't have to study all those minutes? Our random values here have some that went under the hour. So remember, you need at least 60 minutes to call the day a success. So let's say that I wanted to grab a few of these just to point them out so I can encourage myself to reach the full hour. Ones that are super close to the hour but didn't quite reach the goal. I could use some motivation. I may want to build a list of these values. So one thing that I could do is just build a list using standard indexing. So let's see, we want to have fake log, and we want to have this value, this 44. So this is 0, 1, 2, 3. So we have 3, and then we want the next value, 4, 5, 6, 7, 8. Oh, 50. That was so close. So we'll do fake log, and then that's 8, right? So we should have a list of 44 and 50. There we go. Those are so close to making that hour. But this indexing, it's pretty basic, right? There's nothing fancy about it. It's just pulling some values out. Well, lift your finger like you would if you were drinking tea as you type out this next one, because things are about to get fancy. What you can do is type fake log. And in here, we're going to use hard brackets and say 3, 8, and take a look at what we got back. There is our 44 and our 50. It's the same type of the values that we just selected. Pretty fancy, right? So again, using a list as a parameter here is saying, return me a new array with the values from index 3 and 8. Now check this out. It gets fancier. The shape of the resulting array can be defined by the shape of the index array. So this is just a 2-element array, right? Let's build an index array in the shape that we want. So we'll make a 2x2 matrix. So let's do that. So we'll say the index could be named anything. We'll declare an array of lists of lists. So here we go. MP array, we'll say 3, 8, like we had before, right? So we had those two values. And let's just go ahead and grab the first two values for the second row. So we'll have 0 and 1. And then we can use this array for our fancy index. So we say fake log index. And we'll see back we got our 44 and our 50, and we'll get 132 and 122, which I'm pretty sure are the first two, 0 and 1. So we got 44, 50 and 132, 22. And we pulled it out in a special order, and you'll notice that the shape of the array is the same as the index array that we wanted. Ooh la la, c'est chic. Now that we already have our study group log in the right rank, we already have 2 dimensions, let's just go ahead and append this fake log to the study group array. We'll just redefine the study log because remember, these array sizes are always immutable. So we can't just add new elements to them. We need to create a new one. So there's a method right off the NumPy module called append. So we're going to say study minutes because we're going to override that again, equals np.append. And what it does is it takes an array, our study minutes array, and it takes what you want to append. So I guess we want to append our fake log. And then you tell it what axes to append. And we want that on axis 0. I've left an intentional bug here for you to see. Let's go ahead, let's run this. Oh, yikes, look at this mess. All the input arrays must have the same number of dimensions. Now this is a common Stack Overflow question, so I figured I'd save you some time in the likelihood that you might run into the problem like this. So the solution here is just to make sure that the dimensions line up. So we actually need 2 dimensions, right? Our fake log currently is just 1 dimension. So one hack is you could just make this a list of lists. And there we go. And if we take a look at our array now, we'll see that it has the shape of 3 arrays. Awesome. So looking at this, I see that this one here, this is round 2, day 2, or R2D2, everyone's favorite malfunctioning droid. We absolutely have to set that. That is one of the most favorite days of these rounds. So let's set that one. So that would be study minutes 1, 1 equals 360, right? Round 2, day 2 equals 360. Now note here, we aren't using a fancy index. We're using the comma or tuple shortcut. It does get confusing, so you really need to pay attention to what's going on between these outer brackets, right? You need to see if it's a tuple or it's a list. In fact, you can even do multi-dimensional fancy indexing by specifying fancy indexes for each dimension. Now, it's a bit out of the scope for this course, so make sure to check the teacher's notes for more on that. And now, looking at our study log, this is about right. Let's go ahead. Let's run this one more time. I'm going to go ahead. I'm going to go into command mode. I'm going to press D to delete that. And let's show our study minutes one more time. This looks just about right to me. This first round here, I let things slip, right? I got to here. I did that dang Netflix binge of Stranger Things. And then I worked a bit too hard on the second round, right? I did 360 minutes on this day and I burned myself out. But I kept on trucking, and the third time's the charm. It feels pretty realistic to me. This is probably what a lot of people's rounds look like. You have to just keep trying and eventually you'll get it. No matter how many times I learn that lesson, I need to keep reminding myself, stick with it and you'll get it. Now, I don't know about you, but some of these minutes on days where I almost made it, like where they were almost an hour but not quite, like we saw, they would really help me keep going during the times where I was struggling to stick with it. Wouldn't it be cool if we could just somehow pick out the values just under 60 minutes to motivate ourselves, but not have to pick them out by hand visually like we did? Well, you can. And let's do that right after this quick break. Ooh, and also, I'm going to write out some notes on our array creation and appending indexing skills. So let's come up here to where we started doing this. Let's go right here. We're going to go ahead and I'm going to get into command mode, go one above, change this over here to Markdown. And I want to talk about array creation. Then let's also talk about indexing over here. So in the creation, let's talk about random state. And we'll talk about how to append rows. And then indexing wise, let's talk about the shortcut, the tuple one, right? We'll talk about the tuple shortcut. And I also want to talk about fancy indexing. Wow, that was a lot that we covered. Good job. I'm going to swing back after a quick break and flesh this out for better notes, and then I'll share them with you. Why don't you do the same? And I'll see you in a bit. All right, before we get started here, I thought I'd share my notes as a quick refresher. We talked about creation and we saw a new way to build a random grouping of numbers, and we used random state to let us seed the randomness in a way that was repeatable. I have the same random values as you do. That is super handy. And we also learned that you can append a row in a couple of ways. There's even more that we haven't seen here. You can use the NP append method. You need to make sure that it's the same shape. Remember we did that little hack where we wrapped it in a list. And you can create and reassign a new array by including existing arrays as part of the iterable, right? So you can just throw the new array in there and reassign it because you can't change the size. And we looked at indexing, and there's that nice indexing shortcut for the multidimensional arrays. Remember where you could use the comma, so you can say like 3, 4, and that's really row 3, column 4. And instead of having to use the hard brackets, you can use the commas, and it creates a tuple automatically. And you can also index using a list or another NP array, and the values will be pulled out at that specific index, and that's known as fancy indexing. The resulting array comes back, and it's the same shape as what you asked for, but it's very important to remember to look for lists or arrays versus just using a tuple with the comma. All right, so now where were we? Oh, right. We wanted to look at our study log and find hours that were just about an hour, but not quite. So let's get back down into where we did all that work. So here's the study minutes. I'm going to get rid of this last one here. To delete a cell, escape, and then DD. There we go. So we have our study minutes array is all written out. And remember we were using this fake log. So let's start with that fake log because that definitely has some values that we know that are under 60. And remember, that's what we're looking for because they don't count towards the challenge. The concept being there that is if we saw those ones that almost made it, maybe they'd provide a little inspiration for us to stick with it for that next day. So the ND array object is pretty powerful. Just about every comparison operator has been overridden. So let's take that fake log object that we're using because it's one-dimensional. So it's a one-dimensional array, and it's filled with 100 random values. So we'll do fake log, and check this out. I am looking for values that are less than 60 because, there's 60 minutes in an hour. So I can just write that. So fake log less than 60, and what will happen is it's not defined. This might happen to you sometimes. So this is good. I'm glad that this happened. So what we can do is we can go ahead and run kernel and say restart and run all. And that popped up our help because we left the help up there. So I'm going to go ahead and close this. And so what happened is we've got this fake log. And what will happen is you remember that we have these values. So the first one that's there is this fourth. So the fourth value. So if we go false, 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 true, and then looks like again at the 8th there. So there's some more false, 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 true. So what's happening is it's comparing every single one of these values, and it's showing us true where it is. Every value is represented. And any place that we see a true, means that it is true that it's less than 60. And that probably doesn't seem all that handy. Well, that is until you find out that you can do fancy indexing with a Boolean array. The way that it works is that as long as the Boolean array lines up with your other array, any value where true exists will be kept. So here, check this out. So this is what we want, right? We want to say anything from the fake log, and we will use that Boolean array as a fancy index. And there we go. We pulled it all out. Every value that was true. That's exactly what we're looking for, right? These are all not quite 60. Pretty cool, right? We did that filtering all without a loop. You could totally accomplish this same thing by saying something like a list comprehension or even something similar like this really simple loop. So we'll say results equals this. Let's iterate through each of the values. So for value in fake log, if the value is less than 60, then we're going to say results.append value. And then just to get back exactly the same thing, we'll just use it. We'll say NP array results, right? So there's a loop that we had to write, and obviously we got back the same thing. But using a Boolean array index is orders of magnitudes faster than this for loop. And look at the code difference too. Now, something you might be wondering is what happens with multidimensional arrays, like our study minutes array. Well, the good news is it just works. So if we say study minutes less than 60, you'll see back that we get an array, a Boolean array, that is the exact same shape as our array. So that's 3 by 100. And of course, we can use that array as an index. So let's do that as well. So we can say study minutes, where the study minutes is less than 60. Boom. Now, notice that we're returned a one-dimensional array, not our original three-dimensional array. It's all of the values that match. Now, we could rewrite this as a nested for loop of the same type that we did before, right? Like we could loop through each round and then loop through each day and add to our results. But we don't need to do that because this is all done for us without a loop. What's kind of gross is that's a bunch of zeros, right? If we're looking to motivate ourselves, and we really don't want to see these zeros. What we really want to see is anything that's less than 60 minutes and greater than 0. That'd get minutes from days where we worked a little bit at least. So we want to make two Boolean index arrays. Like we want to make this study minutes array, this one, we want to make that array, the study minutes where it's less than 60, and we also want to have another one where the index array is study minutes greater than 0. And then we actually want to have the results where it's a combination of those anded together. You can actually compare arrays together element by element, which is what we want to do. So I'm going to come down here. Let's just we'll go ahead and we'll manually create an array, a Boolean array of false, true, true. And to compare, we use the bitwise operator for and, the ampersand. Now, this is not the and keyword, it's an ampersand. Now, a common mistake is to forget and use the and keyword, and we'll explore what happens here in a bit about that. And then I'll create another Boolean array that we can compare to. So np array, and we'll put in true, false, true. So what happens is we get a brand new array with each element anded together. So remember, when you're checking Boolean logic, both sides need to be true to be considered true. So looking here, we have false and true, and that's false. And then we have true and false, and that, of course, is false as well because they're not both true. And then we have true and true, definitely true. So if we go ahead and we run this, we'll see that we get back a single array with the values anded together, false, false, true, just like we saw. So we could use this result as a Boolean index array, right? Do you see how we can just build the Boolean index array together, values that we want to chain together with all of our other conditions in a series of ands and ors? Before we use it, I do want to show you what happens if you forget to use the bitwise and, as the resulting error is a little confusing at first. So depending on how many times you've joined together logical expressions, your muscle memory might actually accidentally type the and keyword here. So let's do that. Let's put this and keyword here. Yuck, value error. And it's saying the truth value of an array with one or more elements is ambiguous. So what it's trying to do is it's trying to figure out a truthiness of this. And that's what and does. It creates a truthiness. And if it's assuming that we want to have a scalar value, which is not what we want. We want to compare element by element. So if you did want to get a scalar value, if you want to see that everything was true, you would use a.all, and that returns a Boolean, or any, if there's any true in there at all. All that to say, just use bitwise operation. So just go ahead, use a bitwise operation. I just thought I'd preemptively warn you about this as it happens a lot. More in the teacher's notes. So let's build up our index. So we want to have study minutes where the study minutes are less than 60 and study minutes are greater than 0, right? That's what we're looking for. But we want to take caution and make sure that we're careful about the order of operations. This and here is stronger than the less than. So what we're going to get is we're going to get 60 and minutes. And again, we're going to run into the truthy problem that we saw before. So we don't want that. So let's put parens in place just to make sure that we got the order of operations correct. And voila, there we have it. A brand new array containing entries that represent values from our study minutes array that are less than 60 and greater than 0. It's pretty cool, right? And you can see, you can pretty much read that more or less, right? You'll get used to remembering to use the parens and ampersand, but I guarantee you'll forget sometimes. Now, one thing we really should consider is this. Even though we did those minutes, these are minutes here that we spent some time. They don't actually count for completing the challenge. The challenge is to do at least an hour a day. So in reality, we really should set all of these to 0. If deleting these minutes doesn't motivate me, I don't know what will, especially this 58 minutes. Now, even though this index statement, this study minutes less than 60, now, even though that creates a brand new array, if you assign to it, you can do an update. And if we look now, we look at our third row there, we'll see that we add some zeros in where they were not before. Yikes, look at all those. All that time didn't count because I didn't reach that hour. Dope!
Now, of course, that time did actually count. I was learning, but it didn't count towards the challenge. I'll tell you what, this 100 Days of Code challenge totally motivates me, so losing that time definitely will keep me focused in the future. It reminds me that I just need to stick with it. I want to complete this challenge. Speaking of challenges, I'd like to again challenge you to capture your thoughts on Boolean array indexing in your notebook. Remember to think through the possible gotchas that we walked through, like accidentally using the AND keyword or forgetting to use parentheses. If you've ever done SQL programming before, that might have felt familiar. Capture those thoughts a bit. Also, now is a good time to take a moment and review your notebook. Is everything in there clear? If not, please hit up the community and ask your questions. If you're looking to solidify your knowledge, I highly recommend attempting to answer someone else's questions. I can't recommend it enough. By taking the time to explain a concept, you will uncover new knowledge. Give it a shot. It won't disappoint. So far, what we've been doing is returning a new array, but you can actually return a view of the data that you can manipulate. Let's take a look at data views and some more powerful slicing features next. You know how when you don't use a skill for a while, you need to practice it a bit before you can get right back to doing it flawlessly? Like no matter how good you ever were at it, it's where that saying, use it or lose it, comes from. Well, for me, in addition to juggling, that skill I need to dust off is slicing an object. You've probably used slices before on lists or tuples, but if you haven't done it for a while, you could be a little klutzy. This is where practice comes in, and I want to encourage you to practice and test things out. Let's practice a bit of slicing with lists first, just to warm up. And then let's practice with some multidimensional arrays. It's like starting with these practice juggling balls instead of, say, chainsaws.
Jupyter notebooks are excellent for this sort of practice. Oh, actually, real quick, before we get into our slice practicing, let's make use of another great feature of notebooks, notes. So here are mine on Boolean array indexing. So you can create a Boolean array by using a comparison operator on an array. And you can use Boolean arrays for fancy indexing like we saw, kind of like a where clause there from SQL. And Boolean arrays can be compared using bitwise operators. That's and then the pipe sign there is or. And remember, don't use the and keyword. And also remember to use the order of operations. Otherwise, you get that really weird value error that we saw. And even though Boolean indexing returns a brand new array, like a copy, you can update an existing array by using a Boolean index. So let's go down to the bottom here, the very last row. And if you want to clean some of these up, you can. I'm going to get rid of some of these, just DDD in command mode there. All right, so let's make a new list. My go-to list is this fruit. We'll go ahead, we'll get apple, banana, cherry, and durian. All right, now let's warm up those slicing skills. Now, for some reason, I can never remember if slices are inclusive or exclusive. So when I'm not sure, one thing I like to do is just try. You're not going to break anything, right? All right, so let's get a slice of this list. I want to get a portion of this list, like just the second and third value. So let's see. I know that things are 0-based. So I know that I want to get the second one. I'm going to start at 1. And then I want a colon signifying up to. And now, is it inclusive or exclusive? I don't know. I'll try inclusive. So let's see. 1 to 2. No, it's exclusive. Oh, missed it by that much. So if we come back and we say 1, 2, 3, we'll see that we get banana and cherry. So it's like up to, but not including. That's what you can read with this, is like 1 up to, but not including 3. Phew. All right. And then again, if you leave either side blank, so if we say fruit and we go up to 3, we'll get everything up to the third one, which again, not the third one, the fourth one. This is 0-based. And then if you do it at the start, you can say fruit from 3 onwards. So we'll start at the third and go to the end. And there's durian, the cheese of fruit. So just a plain colon then, if you just use a colon, it will give you a copy of the array. It's basically a copy, right, from start to end. In fact, this is typically used as a way of copying standard Python lists. So if I store that in a variable, so we'll say copied equals fruit, and then the colon, so give me everything. And then we go ahead and what if we modify that copy? If we say copied 3, that durian, we're going to set that to cheese. If we set that to cheese, and then we take a look at, let's say, slicing, a list returns a copy. And I'm going to spell slicing correctly. Slicing a list returns a copy. So if we look here, if we look at fruit and then copied, we're just going to make a new tuple of those two so we can look at the values next to each other. We'll see that fruit was not changed when we changed the copy of that. There are actually 2 different places in memory. Okay, and there is a third part to this slice, the step. Now, by default, this is 1. It moves 1 element at a time. But I can add a second colon, representing a step. Let's say that I wanted to get every other one. So we'll say fruit. There we go, apple, cherry, and we skipped banana and durian. So instead of stepping through each element 1 by 1, we went by 2. And you can also use negative to walk backwards, right? So if we say fruit -1, we'll see that it runs backwards. And there we go. I think I'm refreshed. I think I'm ready to start juggling those chainsaws. My de facto test list go-to is this one of fruit. When it comes to creating a NumPy array to explore, the most common way is to use a function named arange, which is very similar to Python's range function, but instead it returns an nd array. So if I say np.arange and I pass it in the ending value there, so it goes up to and not including 20, you'll see that we get all of the values up to and not including 20. So let's go ahead and create a new practice array here, and we will make it np arange, and we'll go up to our magic number 42. And you can actually change the shape property on an array. So we can say practice.shape, and we're going to assign it, let's go 7 rows, 6 columns. So let's do that. And then let's take a look at what practice looks like. Awesome. So let's go ahead and get this number 13 here, lucky 13. So this is a 2-dimensional array or matrix, and really it's just an array of arrays. So we first need to get this row here. So this is 0, 1, 2. So we have practice 2. Okay, let's make sure we got it. Yep. And that's just an array. So we need to get the 0, 1. We need to get the 1th there. There we go. There's 13. And that is entirely too many hard brackets. So let's express it with just a comma. So 2, 1. Awesome. So as you can expect, the ND array is Pythonic, so it too allows for slicing. So if we wanted to start at the third row here and go to the fifth, we could just do this. We could say practice 2 to 5. And there we go. We got just those rows. Awesome. And if we wanted to just get this column here, we could just put comma 3. Awesome. And we can also slice this column dimension. So let's get the fourth column until the end. So we'll say 3 until the end. And there we go. Now we have 15, 16, 17. And then if we wanted to step every other column, we could say 3, 2. And there we just have those 2. Look at that. We stepped right over that column, right? So we skipped right over this column. We limited it, then we sliced it, and we got these 3, and then we skipped over that. So we got just this 15 to 17, 21, 23, 29. Pretty great, right? Now, one thing that'll bite you if you don't know about it is that slices in NumPy don't return a copy. They return a view of our data. Now, this is different than we saw in the standard Python list. So let's explore this real quick. I'm going to write not copied. And we're just going to get everything. We're going to take our practiced array. And I'm going to make a comment here for us later as we look over this. Any slicing of ND array returns a view and not a copy. Okay. So I'm going to go ahead and I'm going to set not copied. I'll set 0, 0, the first one there, 90210. And we will return practice, comma, not copied, just so we can see them next to each other. And we'll see that both of them changed. And that is because this is a view and not a copy, right? It's exactly the same. It changed the original array practice. And that's because not copied is actually what is known as a data view. And as you can tell, it's kind of hard to know just by looking at the representation of the array, that they're views and not brand new arrays. So one way that you can check to see if you have a view is to check the base property. So if we look at this, we can say practice.base is none. And that's true. But if we look at not copied.base is none, we'll see that that's false because it is copied. And then also that base is set. If you say not copied.base is practice, we'll see that that's true. So you can always see where it was copied from. And there's also a property called flags on arrays, and it's a dictionary. And one of the keys is called own data. So you can check that as well if you wanted to. You could say practice.flags. Does this own the data? And that one should be true, and not copied does not own the data. It is a view. So data views are important to understand and be aware of, as you don't want to accidentally modify a structure that you didn't intend to. Data views are part of the trick of how quick and seamlessly you can rearrange data in NumPy, so you will see them used in the wild quite a bit. Now, the one major and not initially intuitive place where data views get created is in slicing, like we just saw. So I'd like to make sure that you recall that when you slice an array of any shape, that you are creating a view and not a new array or copy, as happens with standard Python lists. A view references the same values in memory, while a copy would be a brand new space. Using a slice or view is handy as you can pass only part of the array around for processing, but not require the entire array. By not creating a new array, we are not only saving memory, but we're also allowing a reshaping of the array. We're allowing portions or slices of the array to be modified. Let's take a look at some more data view creating functions. And actually, I'm going to take some notes on slicing and slicing multiple dimensional arrays specifically. I'm also going to make sure to document that little data view gotcha. Let's review that right after this quick break.
We were able to change the shape of our array by setting the shape property directly. Now, this is handy when you want to permanently change the arrangement of your data, but that's not always going to be the case. You'll find as you work more and more with datasets that you're going to want to temporarily bend and mold a view of your data to work with, but leave the original one intact. This is where those data views, like the ones that we got from slicing, come in handy. There are a ton of ways to manipulate your data. Let's take a look at some of the more popular techniques, and I'll show you how and where to learn more.
Ooh, first though, let's compare our notes on slicing. So slicing works a lot like normal list slicing. It's very Pythonic, and you can use commas to separate each dimension slice, right? So you can slice the dimension. And it always returns a data view. Remember that, not a copy. That's very different than it, but it's important to know. And you can always access the base object using ndarray.base. Awesome. So remember, we changed the shape earlier. We changed the shape. Where did we do that? We just changed it right here, specifically once, and we changed it permanently. We changed the original practice array that way. So you can actually create a view instead by using the method reshape. Let's remind ourselves what a practice array looks like. It's a 7 by 6, right? So all the way up to 42. So let's assume that we wanted to have 3 rows, and that would be 14 columns, right? So we will do that. We'll say practice view equals practice dot reshape 3, 14. And just to make sure, we'll get practice, and then we'll get practice view. We're just going to pop these out here to take a look. Figure this is a handy way to do it all in one line. And then we'll say practice view dot base is practice. Okay, so we're going to make a view off of that practice arrays. So there we go. We now have a 3-dimensional array instead of a 7 by 6. And you'll see that at the end here, we've got true. So it is the base. So the view isn't taking up any more memory. It's just pointing to the original data, which allows you to save space. And it gets things in the proper shape as you need without wasting space. Reshape also has a great feature. It'll infer what you want if you pass it a -1 to any dimension. So for instance, let's say practice.reshape, and we're going to give that, the first one I don't know. All I know is I want 2 columns, right? So you'll see that that inferred 21. If we go here and we say .shape, see what happened there is it got 21 by 2. Awesome, right? Now, a very common reshaping that you'll want to do is all of the elements in a single dimension. Like you'll have something shaped up, but you just want a single dimension, which you could reshape with just a -1. But there's a better way. So we can say practice.ravel. And you'll see what happens here is we get a single dimension, and it kind of unravels all of those dimensions. Now, this is a view and not a copy. If you do want a copy, you can use the method flatten. Flatten creates a copy. How do you remember that, though? Well, the answer is you don't. Like most things in this programming world, you just need to remember that you need to lean on documentation. NumPy's official documentation is pretty good. So let's take a quick peek. I have this page bookmarked, and if it were an actual book, the page would be worn. It would have tons of highlights and circled entries and lots of coffee stains. NumPy's reference guide is very well indexed on the oracle of your choice. So I'm going to use Google, and we'll say array manipulation, and we'll do NumPy. And this first hit here is what we want. So let's do that. So here's the page. Usually whatever you may be trying to do manipulation-wise can be found here. So let's scroll down a little bit, changing the array shape. Looky here. Here's reshape. Here's ravel. And here's flatten. So let's click into ravel here. And it returns a contiguous flattened array. Awesome. Contiguous meaning one element after the other, no space in between. And then flattened meaning the dimensions are removed. And a one-dimensional array containing the elements of the input is returned. A copy is made only if needed. So there we go. It's a data view. We could just look up this documentation and know that it's a data view. These docs do end up working a bit like a Wikipedia hole, where one topic leads to another one, and before you know it, you've read half the internet. So just a word of warning. This See Also section is a bit of a learning rabbit hole. So I want to point out that I really like the notes and examples that these pages provide. Seeing the examples show the function in action, and oftentimes there's extra information tucked away. Like, for instance, here it says, this is equivalent to reshape -1, which we just talked about, right? Remember how reshape takes the -1? If we wanted to ravel, we could do that. So here you go. Here's NP ravel. 2 arrays, there it is. And it's saying that it's equivalent. There's reshape -1, and there's ravel, and it's doing the same thing. There's some extra talk in the doc here and in several functions about order. This deals with the way that we talk about indices and how they're stored in memory. Now, this is out of the scope of this course, but I do want you to know that all of the functions that we are using use C as the ordering default. And actually, in most cases, you'll see that that makes sense. If you'd like to learn more about index order, check the teacher's notes. Okay, let's go into our hole here and let's take a look at flatten. So let's assume that we found this page first. And here in the description, we see very clearly that this returns a copy of the array collapsed into one dimension. And if this wasn't what we wanted, we could also come down here and we could see that ravel would probably work. And there's another quick way to get at this information if you don't feel like leaving the comfort of your notebook. So let's go back to the notebook. And I totally get not wanting to leave the notebook. There is no telling what's going to distract you if you open up that browser. Am I right? So the NumPy team did something super clever and built a search engine for docstrings. So imagine this is a few days in the future and you're in your notebook and you want to make sure that you get that one function. You know that one, right? What's the name of that one again? The one that makes the array flat, but it's a view and it's not a copy. What was that called? Well, I'm going to search for it. I'm going to look for it. So I'm going to np.lookfor. I'm going to look for flat because I remembered it had something to do with flattening. So here's some stuff. Oh, here it is. A contiguous flattened array. That was at ravel. And let's just make sure that that's right. So I can come up here and I can say np.ravel and do a question mark. And is that what I was talking about? Yes, a contiguous flattened array. So check this out. It's the actual docstring. So it's got the parameters. There's the returns, there's your C alsos, there's the notes that we talked about, and here's the examples. Pretty rad, right? This look for function is super handy for not getting interrupted and or going down a documentation internet hole. So anyways, let's get back to that bookmarked page and explore what else is on here. So I'm going to come back up here and I'm going to go back and back again, get back to our list. Awesome. So transpose-like operations. Transposing lets you flip the order of the array around. It switches the rows with the columns. So if you had 4 row by 3 columns, transposing would give you 3 rows by 4 columns. The same data, it's just flipped around. So you'll see this referred to with the property of capital T here. So let's go ahead, let's get in there because this is a little strange and you'll see them. Here's a great example. So we've made a 2-dimensional array. We've got 1, 2, 3, 4 as rows. And if you do x.t, and again, that is a property on there. Now it's flipped, right? So now we have 1 and 3 and 2 and 4. So we have 1 and 3 as the rows and 2 and 4 as the columns. It just transposes it. This is handy for quite a few equations that require you to invert a matrix. I just wanted you to understand what the strangely named property T is doing. You'll see this thrown around quite a bit in examples and blog posts. So let's go back and scooch down this document a little bit here, changing the number of dimensions, changing the kind of array, joining arrays. This is important here. Much like we can split and join on strings, this is a similar idea. It breaks apart and puts together multidimensional arrays. Now, the thing that I want to point out here is that this H prefix, that stands for horizontal, V is for vertical, and D is for depth in a 3-dimensional space. So again, these methods are all handy for when you want to stitch together the proper matrix for a particular equation.
There are a plethora of options for manipulating your arrays to match just about whatever shape you might need. There are tons of well-documented recipes for adding rows and columns. I'm glad that you've got access to that array manipulation page in the documentation. I'm sure it will serve you well. It has me. Why don't we both go and add some notes to our notebook? Make sure to include a link to that page. Also, don't forget to take note of that super handy method that we talked about to search the documentation, look for. I'm going to review that manipulation page and just kind of jot down anything that I want to remember. Now, I know these manipulation methods have been a little abstract, and it's kind of challenging to imagine why you might need to use them. This is one of those cases where it's handy to know what you're capable of doing when it comes time to use your skills. And I don't know about you, but I always disliked that part of math class. I was always like, but why? Let's see if we can't answer that question. Let's take a break and swing back and start exploring some of the more powerful math features of this library. You've done an excellent job learning all about NumPy arrays. You can create, inspect, and modify them. You can manipulate them into new shapes, and you can filter out the values you don't want. And now, I'd like to take some time to show off some common use cases for these arrays that we've been getting to know. But before we dive in here, I'd like to take a second to discuss a phenomenon known as imposter syndrome. Imposter syndrome happens when you doubt your skills, and you feel like you really aren't a pro. You feel like a fraud. You feel like everyone else knows more than you. It's an unfortunate and quite common feeling, and I want you to know that you aren't alone in experiencing it. And I especially want you to know that you aren't actually a fraud and that you can do this. Because of the numerous use cases of NumPy arrays, you're bound to see lots of math equations and formulas that you don't yet understand. You might have learned once and have forgotten. What happens is you think, man, I only know this much stuff. Look how much everyone else knows. But here's the thing. Very few people know it all. They all know their own little bit. And you can and will learn the extra little bits when you actually need them. This is important to remember. That feeling is bound to happen to you, and I just want you to be ready for it. Approach it like, hey, I'm not sure how to do that yet, because you will learn it. And look at you, you're doing great already. I want you to approach things with the growth mindset. Check the teacher's notes for more on that. We're going to be doing a different type of programming than we've been doing up until now on our Python journey together. We're going to be doing what is known as array programming. Instead of our typical way of looping through a collection of data and pulling out values one by one to perform operations, what we do in array programming is to perform the operation on the entire set of values all at once in one fell swoop. Not only is it faster, it's also expressed much more concisely in code. Array programming code often ends up looking a lot like a math equation. We've talked about how an array is referred to as a vector and a two-dimensional array as a matrix. Well, the reason for that is because we use these arrays to represent their mathematical equivalent. It's probably a little too abstract. Let me show you what I mean by that statement. Oh, I got an idea. Let's do some linear algebra. Why the long face? That doesn't sound fun? Did you forget how to do it too? Don't worry. All we have to do is set up the equation properly using the correct layout, and NumPy is going to do all of the work for us. I had a moment recently where I had to take back one of those famous quips that we all make at one point in our lives regarding stuff we're learning. You know the one. When am I ever going to need this? Oh, probably not very surprising to you by now, but this example involves tacos. There's a new taco food cart that just opened by our office, and I like to share my love of tacos with my coworkers, so I often offer to do pickups for the office. Now, if you've ever been in charge of a taco run, you know that one of the main problems is that you're never quite sure the price of the items. So I'm usually just like, just pay me later, and I'll put on my credit card. And sometimes determining that price from the total is easy. Like in the case where you have 2 tacos and the total's $3. You can do that kind of math in your head, right? So you might not even know how you did it, but you know that a single taco costs $1.50. That's pretty simple, if that was the only item on the order. But that's never the case, right? So I know one of the larger orders I bought was 4 tacos, 1 burrito, 2 horchatas, and 2 Mexican Cokes, and the total was $20.50. Nothing is better than a Mexi Coke in a bottle. Real sugar. With that information, though, I have no idea how to figure out the price breakdown. It's definitely not as easy as that 2 tacos equation that we did in our heads. And this is because there are so many other variables now. But I seem to remember from math that if you have enough equations, you should be able to solve them. So let's see, do I have more data? Of course I do. I went once and I got a burrito and a Mexi Coke, and that was $10. Oh, and another office pickup. I did 6 tacos, 1 horchata, and 2 Mexi Cokes, and that was $14.25. Now, one thing I remember from math is we're going to need to make sure that everything is lined up. That means I need to make sure that I enter a 0 for all the items I didn't purchase, and we get some nice looking equations here. Now, if that doesn't look like a math equation to you, what if we change those variables to their typical looking form? Don't let those freak you out though. Remember, they're just representing tacos and burritos and whatnot. So really, this left side here kind of looks like rows and columns almost, doesn't it? In fact, let's make the type of food the heading here. And what we have left here is the number of items, or the coefficient. In mathematics, to denote a matrix, you will see hard brackets like this. And for our totals, we can consider this as a single dimension array, or as it's called, a vector, a row-based vector to be precise. And with our system of equations as a matrix and our totals as a vector, we should be able to solve for it. There are definitely rules and ways to go about solving that system of linear equations, but what do you say we let NumPy do the work for us?
In the teacher notes attached to this video, I've added the equations to create our matrix. So I'm going to copy and paste it here in the cell. So here is our orders array, and that's our matrix, right? That's what it looks like. It's an array with a rank of 2. It's got 2 dimensions, and each row here represents an order, right? And this is the number of tacos. This first column here is tacos, right? And then the next one being burritos, and then horchata and Coke, right? And now we need to get our constant prices. So that's also in the teacher's notes. Let me just paste that here. So these are the totals of what came across. Scroll this up a little bit. There we go. So we got our $3, $20.50 for the second order, 10 and $14.25. So really what we've done here is to build the math equation, right? Well, now for the awesome part. We don't actually need to know how to solve this. We just need to know that it's a system of linear equations that we're trying to solve for. And we also need to know that there is a module in the NumPy library for linear algebra. It's shortened to linalg. And here is the beautiful method. Solve. And we pass it our coefficient matrix, which was our orders. And we also pass it our totals. So we say totals like so. And then let's go ahead and take a look at what prices is. Look at that. $1.50 tacos. We knew that. $8 burritos, $1.25 horchatas, and a Mexican Coke for $2. Please, no tariffs. That Coke is more expensive than a taco already, but well worth it. Wait a second. If we have this solution, I think we should be able to verify it, right? I mean, if we just plugged in these prices to the equations, it should produce a total. Right? Shouldn't it? So let's see. Naturally, in Python, I guess we would just loop through the matrix and then loop over the prices and multiply them together, and then we'd add them together, right? And that should produce the price. Now, we could definitely do that, but let's remember that one of the benefits of array programming is that we don't need to rely on loops. Also, if there's a mathematical way to do something, most likely there's a way to do it in NumPy. Now, what we're talking about here, multiplying matrices with vectors and then summing them together, is actually a common math practice. And it's referred to as the inner product. And it's usually represented with a dot. So you would say like A dot B. That's exactly what we would have done in a loop, but expressed in mathematical terms. The notation, right? So in Python, though, that dot that I just created, that doesn't have any meaning. So instead, we can use the @ sign, like so. So if we say orders at prices, let's see what happens. So check that out. That is what our totals were. Look at that. It adds up. So it took these and ran them through the equations and ended up with the same totals. So we know that it works. And so really, this is shorthand for orders dot prices. See, it's the same thing. Pretty cool how we can use these shortcuts to build and solve equations, right? It's super powerful. And I'm glad that you have all those array manipulation powers in your bag of tricks.
As I know you're aware, linear algebra has many more applications than just taco price calculations. It's great for times, like we just saw, when you're trying to solve for missing variables in a bunch of equations. And remember, this is just one formula. There are so many more. And many of those formulas that are available for you to use will most likely not be familiar. Remember, that's okay. No one knows them all. You'll learn them as you need them. Don't let the options overwhelm you. Let them make you feel empowered. You don't need to know how to solve them yourself, and that should feel great. That linalg.solve function is a bit of an abstraction. It really is doing all that work that you would have had to do by hand, like you might have done in math class. It's very similar to how we could have written that dot loop. There's actually a function that does all the heavy lifting for us. What do you say we take a quick look at some more common vector-based operations that you'll encounter as you progress? let me show you off NumPy's universal functions, or ufuncs. First though, let's take a quick break, and why don't you jot down some thoughts and notes about what we just accomplished, all without using loops. Oh yeah, quick reminder, make sure to check out the teacher's notes on this video. I've dropped a lot of information about where to learn more about linear algebra, if that got you reinvigorated. And like I said, it's no big deal if it didn't. There are many more use cases for NumPy. See you soon, and we'll compare notes. When we perform operations on our data all at once without using a loop, the operation is said to be vectorized. It's not only faster, but we usually end up writing fewer lines of code. Out of the box, there are quite a few NumPy functions that are available for you to use that are already vectorized. These are referred to as universal functions, or ufuncs. When there's one of these universal functions available for what you're trying to accomplish, you want to ensure that you make use of it. Before you start writing a loop, look first to the ufuncs. Let's take a look at the more popular examples of these universal functions, and then I'll show you where to learn more.
Here are my notes from the linear algebra exercise that we just did. So there's a module for linear algebra, and it's linalg. There's a link to the documentation if you want it. And you can also solve for a system of equations using the solve function, which was amazing, right? We just made that two-dimensional matrix, and we had a constant row vector, and we were able to solve for each variable. And then we were able to double check using the inner product, or dot. Again, there's a link to the documentation. And again, in Python 3 and up, you can use the @ sign there to produce a dot product of two arrays. Awesome. Some of that abstraction that was going on in the linalg solve function was using some vector math, right? And this is super common in just about every direction you head with NumPy. You'll want to perform some operations on two vectors together. Let's take a look at what that looks like real quick. So how about we make a couple of example arrays? Let's go down here. And let's make some example arrays. So for our purposes, we'll make one-dimensional arrays. And let's unpack some into A and B, and we'll just use a split method. So we'll say np.split. Let's see, let's make an array of 1 through 10. So we'll say np.arange, and remember it's exclusive, but we'll start with 1 and we'll go to 11, up to and not including 11. It's exclusive. And the last parameter of split is how many you want. So we want to take 1 through 10 and split it into 2. And then let's just double check we got what we wanted. We'll print those out. Awesome. So we have 1 through 5 and 6 through 10. So what happens when we add these together? Now, I know in regular Python world, this would make a new list with all of the values, right? Let's explore what happens when we do this with nd arrays. So we'll say A plus B. That's pretty cool, right? It does vector math. It adds each element as they line up, right? So we have 6 plus 1 is 7, and we have 7 plus 2 is 9, and 8 plus 3 is 11, and so on. So the plus operator has been overloaded for these nd arrays, and I bet then the other ones must be too, right? So what happens if we do A minus B? We get an array of -5s, right? 1 minus 6 is -5, 2 minus 7 is -5, and then of course the order matters, just like in math, right? So if we do B minus A now, we should get all 5s. Awesome. So then does that mean that we can do A times B? It does. Awesome. And so then what do you think happens when we add a scalar to that array? So what happens if I do A plus 2? Interesting. Look at that. It took the right side, this 2, and it applied it to every value. So 1 plus 2, 2 plus 2, 3 plus 2. It's almost as if there was a right side that was the same size, something like this. So there's this method that you can do. You can say np.repeat. So we want to have that's 5. We want to have an array of 2s that's 5 long. So would look like that. And so basically the same thing is happening if we did A plus that, right? We get the same thing. So it's stretched that too. That's pretty neat, right? So this ability to just stretch the scalar value across all of the items is called broadcasting. The value 2 is broadcasted across the array named A. Broadcasting is handy because we don't actually need to create this array, right? We don't need to do that ourselves. The equation automatically assumed what we meant. Now you'll see broadcasting relied upon quite a bit. These operators have all been overloaded and are actually using universal functions, or ufuncs. And remember, ufuncs are vectorized. See how we didn't have to loop through the array ourselves? It did all that looping behind the scenes for us. Let's pop over to some documentation for these ufuncs. One of the great things about this weird naming is I can just search for ufuncs, and I'm going to find the documentation. There it is, the first hit. My wife also says that to me every time I come back from the gym. She says, "Ooh, ufuncs." That joke really stinks. And I apologize in advance for making you think about that bad joke every time you hear the term ufuncs. This is a helpful page as it details the rules of broadcasting as well as universal functions, and broadcasting, again, that array stretching that we just saw, which is super important in vectorized operations. Again, are no looping functions. So in the table of contents on this page, which is not showing because it's so big, I'm going to shrink this in one. There we go. So here's this table of contents. Over here, we're going to take a look at these available ufuncs. Cool. I'm going to blow this up one more time now that we're here. And so here's the available ufuncs, and what we can look about, here's the add. We just did that. Let's go ahead and click into it. So you'll see that if you use the style of calling the function that we have extra arguments. They're optional, right? So they're where equals true. For example, you can choose which specific elements to operate on, okay? And you can choose to cast it to something else as well, if that's what you're looking for. But these first two arguments, this x1 and x2, that's the left and the right that we were talking about. So you'll notice here in the description that it says that they must be broadcastable, which is defined in those broadcasting rules that we skipped over just a bit ago in the ufuncs documentation. Let's scroll down here because there's some great examples. So you'll see that you can add just fine. You can add scalar values together. So if you have a scalar plus a scalar, it returns what you would think it would. And the second one is showing another example of broadcasting, which I think we should explore because this is showing a 3 by 3 and then it's adding by a 3 array. So let's go ahead. Let's copy and paste this. So I'm going to copy this over to our notebook, and I don't know about you, but sometimes I have a hard time seeing what it is exactly that's happening. So I like to say x1, x2. Now we can take a look at both of them, and I'm going to move this down here. One of the great things about the notebooks is it lets you keep those chevrons in there, those greater than signs. It's not going to bother anything. So that's awesome for copying and pasting. So there we go. So we have our array here and this other array here. And what's going to happen is we are going to add those together. I'm going to get rid of this. We're going to add those together. So let's take a look and see what happens. So it broadcasted this array over each row. So 0 plus 0, that's 0. 1 plus 1 is 2. 2 plus 2 is 4. And then again, it took that to the second one. It broadcasted there. So 0 plus 3 is 3. 1 plus 4 is 5. See how it's going there? It's pretty cool, right? And also, scalars can be broadcast to multidimensional arrays. So if we also do np add, 2, we can see that the 2 is added to every single one of the values. See how it's broadcasted to each and every value? So let's switch back to our documentation. So there's some more math operations. These are what was being called when we were doing the overloading, basically, right? So there's subtract, multiply, divide. Let's get through all these. Square root, that's handy. All right, trigonometry functions. Super handy. That is, if you need them. I know that trig can trigger some people. Don't let it. The important thing to remember is that you can run these functions against all of the values in your array all at once, which is super powerful. If you need to use these, you'll be very happy. So we look at these. Here's hypot for hypotenuse, the old a squared plus b squared equals c squared. This creates an array of all the c's. Pretty nice, right? Here's some low-level bit twiddling functions. Again, handy if you need it, if you're dealing with binary data and you need to move some stuff around. And then here's some comparison functions. And this too is operator overloaded. Remember when we used the less than sign to see all the minutes that were less than 60? Well, that was using this less ufunc. And then when we wanted to check that that comparison was true and it was greater than 0, we used logical and. Oh, Look, here's that warning about not using the word and or, but instead using the bitwise and, or signs. And here's another warning that we saw where we needed to make sure that the order of operations was used, right? So it's again warning about the fact that to and a is evaluated first. Awesome. This is reminding you to do like we just learned. Remember when we used that less than 60? The 60 is scalar, and we just broadcasted that to each and every element for a comparison. Broadcasting is pretty straightforward most of the time. It's usually either a scalar or a row like we saw. However, if you end up seeing it happening and scratch your head about what's going on, you should bring this page back up, right? So bring this page back up because up here at the very top, sorry for that scrolling, that might make you sick. This broadcasting here, these rules are detailed out and it's super handy if you can't figure out what's going on. And it's nice to review from time to time. I don't want to overload you with these rules. I just want you to know where to find them defined. And that's ufuncs for you. Super handy, right? You definitely want to lean heavily on them. There is optimization that happens at the core NumPy level, and you can actually even write your own. Check the teacher's notes for more information. So, why don't you jot down some notes about ufuncs and vectorization in general, maybe toss in a couple words about broadcasting, and I'll do that too, and after the break, we'll review them and check out some more handy routines. So here's my notes on ufuncs, or universal functions. They're commonly needed vectorized functions, again, which allow you to operate element by element instead of using a loop. And standard math and comparison operators like plus, minus, multiply, and greater than, equal to, they've all been overloaded so that they can make use of vectorization. And values can be broadcasted or stretched to be applied to the vector, right? So remember that 2 got stretched all the way across a scalar, or we did it by rows. Awesome. So we saw some super powerful ufuncs, and let's go take a look at some higher level routines that make use of them for common tasks. Now, all this talk of trigonometry is making me want to go back and take a look at one of those first multidimensional arrays that we created, that students' GPAs. That was way up here at the top, wasn't it? Let's get back up here. You've done a lot in this course. All right, so here we go. Here's our student GPAs. Let's go ahead, let's take a look again one more time at what that is. So we'll say students, GPAs. Right, so the 0th row of this is me, and then we had Vlada, and then we had Kwesi. Awesome. One thing that we can do is we can find out the average or mean of this data. So the way that you do that is just call a function on it. Say students GPAs dot mean. Oh, whoops. That returned all of our scores averaged together, which 3.805 is not bad for our cohort average. However, I was hoping to get a mean of each row of these students. Now, the great news is that there is an axis argument that we can pass, and it will do what we want. The parameter, though, has been known to trip people up. So let's focus a bit on the issue. So we have a 2-dimensional array. Our first dimension is students, and our second dimension is of GPA by year in school, right? So we want to have the mean of the second dimension, right? We want this dimension. This is what we want. The GPAs is what we want. So that would be access 1. Remember that they are 0-based, so access 0 is the other way, so access 1 is this. So let's go ahead and do that. Let's say the students' GPAs.mean, and we'll do access equals 1. And since we've got 3 results here and we only have 3 students, we know that it did the right thing. It went across and did the average there. So there's 3.69. Let's go ahead and say 3.7. And then there's 3.75 and 3.97. And by the way, that 3.7 didn't really mean anything. Now, a common mistake is that people think that they want to work with each row. So they choose the access 0. But really what happens with access 0, let's go ahead and do that. We'll say access 0 is it ends up going this way, right? So it's averaging access this way because it's reducing the values. It's summing all these values up, but we want to go this way. So when you think about the access, remember it's what direction you're moving in. Totally common hiccup. Just remember to imagine the function happening across a dimension. Now, you might want this sometimes though, right? This access 0 will give you the average of all students by year. That's what you want. And then if you want to, you can do access 1, and it gives you average of all years by student. This type of function is known as a reduction operation. The function reduces a set of values down to 1. The concept is that there is a function that takes two values, a total value of all operations and the next value in the array-like object. It performs the operation and returns the total to be used in the next iteration, recursively. Might sound complicated, but it's actually what you would do in your head if I asked you to add up all the values in this list. It's probably easier to just see it in action, so let's do it. All functions that are ufuncs have the ability to do this built into it. Here, let's go back down to the 100 Days of Code study minutes list. Where is this at? Let's go down to where we have the very last one of them. Here we go. Study minutes list. Here we go. All right, so I'm going to add one below this. Remember that our study minutes array is a two-dimensional array. The first dimension represents rounds or attempts, and the second dimension is the minutes per day, and there are 100 days. So let's simplify things first by using a single dimension. I'm going to grab the first round here. So we'll say study minutes, 0. Now, if I asked you to total these minutes up, I bet you'd just start adding and remembering like this. You'd say, okay, so 150 plus 60, that's 210. And now I go 210 plus 80, that's 290. And then I take the total of 290 and I add 60 to get 350 and so on and so on and so on. That is reducing in a nutshell. If we continue all the way through the array, we'll have a total. Now, I said that all ufuncs have the ability to do this reduction. And the way they provide this functionality is by exposing some functions off of the ufunc itself. That sentence was pretty funky. What we were doing was adding all the values up. In that case, the ufunc that we'd like to use is add. So let's do it. So we'll say np.add.reduce, and then we'll pass in our array. And there it is, 440. And it did just like we were doing. If you want to actually see each step, there is a function for that available too on each ufunc. So np.add.accumulate, and this will show you each step through. So if we do, again, if we do study minutes 0, we'll see that we have 150, 210, 290, 350, and then actually you'll see all of the zeros adds that we had to do. And yikes, you can see the waste of time that we made this do by adding all the zeros. We could have filtered them out. More in the teacher's notes. Now, we want to get the sum of all these values together, and there is, of course, a routine that's super common, and it is called sum. So if we just make this np, well, let's make a new one. Let's save that there for us. np.sum, and we say study minutes 0. We'll see that we get 440, which was exactly what we did when we did the reduce. And the reduction works on multi-dimensions as well. So we can just say np.sum study minutes, and it will get, wow, 10,000 hours. Must be a pro. I think that's what Macklemore said, or Malcolm Gladwell. I can't remember which one said that. Reduction functions will almost always define an access parameter. So in this case, we want to see the sum of all minutes by round. So that's access 1. And there we know that we did it right because there are 3 results turned back. And 440 was what we got, we were getting for the first one. Awesome. Pretty handy, right? And as you can imagine, that mean function that we were just using is probably using this sum function under the covers. Since to calculate the mean, what you do is you add all the values and then divide by the total amount of values. But what's nice is that you don't need to remember that formula. Now, even though it
is simple, it's been abstracted away for you by simply calling the mean function. You'll find that there are lots of formulas abstracted away for you in the library. In fact, let's pop over real quick to another popular page in the documentation. I'm just going to Google statistics NumPy. Here we go. There are tons of functions available for you here. Since it's statistics, a bunch of these are reduction-based. They reduce all the values down to 1. And here's one that you'll see everywhere, STD. And while it's actually known to spread itself around, it's short for standard deviation. Here, let's pop in. So it computes the standard deviation along the specified axis. It's the measure of the spread of a distribution, which is great. And if we scroll down here in the notes, we can see that this is what has been calculated. This is the formula. Now, I kind of remember doing that in math class, but the point is here, you don't need to know how to calculate it. You want to know why to use it. As we discussed when we first introduced the grade point averages, or GPAs, people struggle with math concepts when they are first introduced to them. And I'm under the belief it's the memorization of the formula that most people struggle with. Typically, that's what you're tested on, not the actual way to use the function in the real world. Current learning science says that if you don't use it, you will lose it. So if these equations feel a bit rusty and you haven't used them recently, don't fret, your brain is just working correctly. Most of the time, you hardly get a chance to see why in your math class. You just focused on the how. So with that said, let's pop up a couple levels here in our bookmarks to routines. This page here is a really great overview of how powerful this library is and a great look at some common abstractions. So if we look down here, here is some discrete Fourier transforms. Here's some financial functions, linear algebra, input and output, logic functions, polynomials, statistics. There's a lot in here. Remember, you don't need to know all of these. Just be aware that what you're trying to do most likely already exists. As you can see, there are tons of directions that you can head with this library. So stand on the shoulders of giants who built things out for you. We talked way back when about how all sorts of different libraries accept and return NumPy arrays. Let's take a quick break and take a look at one common use case, plotting values on a graph. Well, that is right after we jot down some notes. Why don't you talk a bit about some common routines that you saw and talk a bit about reduction?
Just about every Python data library that you come across is going to accept and produce NumPy arrays. Let's take a look at a common use case, plotting our data graphically. Let's go and get matplotlib installed.
So here are my reflection notes, but before we review them, let's multitask. We need to install matplotlib. So let's flip over to our terminal, and we will stop the server with Control-C. And do I want to shut this down? I'm going to click yes to shut it down. We go back at the prompt, and we're going to type conda install matplotlib. And as that starts happening, we are just going to go and flip over back to our notebook. I'm going to say, okay, it's still up. So it says connecting to kernel. That's fine because the server's down. So let's take a look at this. So some common mathematical routines are exposed so the formula could be abstracted away, right? That was awesome. So we saw mean was like that, STD or standard deviation was like that. A note here of reduction functions take a dimension and it will collapse. It will reduce across that into a single value. And that axis parameter is one that's a little bit tricky. Good thing we made note of that with some examples. Awesome. And it works across the dimension. So that's the common routines. And I did another little section here about the universal functions. So here we go. Universal functions expose a function to reduce an array to a single value. And there's also a function called accumulate, which is nice because you can see things as it accumulates. Let's see how we're doing with our server. Oh, shoot. Yes, we want that to install. I was trying to be a little too fast there. All right, cool. Here, we're good. So let's go ahead and let's start that notebook back up. Jupyter Notebook. And we should be able to just do it over here
if we come back here and we say kernel, restart and run all, here we go. Back to it. If you haven't used matplotlib before, it's a wonderful, versatile, and quite popular graphing library. There's more in the teacher's notes if you'd like to learn more. So I'm going to come up here into my imports, and I am going to add matplotlib. So we'll say import matplotlib.pyplot. And keeping things lazy, it's called PLT typically, as PLT. Awesome. So what can we do with that? Well, what do you say we create a graph that shows the students' GPA's matrix? So let's get down to where that was at. Here we go. Let's get rid of a couple of these. DD. And I'm going to come here. We should probably convey the way that each student performed over the year. Now, choosing which type of graph to get your point across the best is an art form in and of itself. Now, one effective way that I've seen this expressed is by using what is known as a box plot. So what a box plot does is it shows the range, the maximum and the minimum, and the various quartiles and the mean, all in one graph. Well, the best way to explore anything is just to explore it. Let's do it. Off of the pyplot module, there is a function named boxplot. Plot boxplot. And it takes an array. So let's give it our array. So we'll say students GPAs. And then I'm going to go ahead and do plt.plot. That will actually draw it here for us in our notebook. Check this out. Students' GPAs is not defined. Oh, I wonder if that's because I ran the line. Let's try that one more time. Start and run all. That looked like it worked. Sorry about that. Drops us down at the bottom too, so we got to get back up to where we were. There we go. There's our graph. Look at that. It looks like we're doing the right math, but it's along the years, right? So this is 1, 2, 3, 4. If you remember what our student GPAs look like, fourth was all 4, and these was 4, 3, 2, 3, 9, 6. Let's just make sure. Yeah, that's what's happening here. So it's along the years instead of along the students. This is also a perfectly fine way of looking at things, but it's not what we're after. So this bottom whisker here is the minimum, and the top whisker is the maximum. Here's the interquartile, and this is the median here. It's a bummer that the box plot is graphing along the columns. Oh wait, wasn't there a way to switch the axes of the array? Like you could go from a 4 to 3 to a 3 to 4? Pretty sure it was on that array manipulation doc that we linked to in our notes. Now, if you don't remember how to do this, why don't you go and find that? Give me a pause and see if you can't find it in the documentation, and get this graph showing what we want. Go ahead, pause me. Did you find it? It's transpose, so .t, right? On all arrays, it will actually transpose and it will switch the order of the array. So let's run that one more time. Beautiful, here we go. So we've got the 3 students, this is me. I was all over the place. Kwesi doing good, like we said. And here's Vlada doing well as well. Got so much better from the start. So what do you think we could do with our 100 days of code study minutes? I know one of the questions that I get often is, how much time do you actually spend doing it? Because, you know, sometimes it's hard to stop once you get on a roll. I'm definitely one to overdo it. So let's go down to our study minutes. I'm going to scroll down here, right about here. One way to tackle this is to group your data, right? Now, there's a type of graph known as a histogram that will group your data into bins or buckets and then display it. It's pretty perfect for what we need, actually. So remember that we dropped the values that were under 60. So we really just want values that are greater than 0. So the name of the function is hist, short for histogram, not like what a cat does when you try to be nice to it. So we're going to put in here all of the minutes that are greater than 0. Actually, why don't you do that? So I'm going to leave a little to do here for you. So we're going to say pass in a one-dimensional array of all the minutes that are greater than 0. I want to put this on a new line. So you got that, right? You can do that. Go ahead, into this hist function, pass in a one-dimensional array of all the minutes that are greater than 0. Go ahead, pause me. You got this. How'd you do? Did you get it? So we can index our study minutes array with a Boolean array, right? And we're going to use broadcasting here because we're going to broadcast this 0 using this comparison operator. And that will give us a one-dimensional array of all the values. And so we can say plot. Bam, look at that. There's some buckets that got defined by our data. So 25-ish, maybe 26, 27 times, we were in the first range of 60 or so. And you could tweak this actually a little bit more, but I think that this gets the point across pretty well. There's times where I was down here in the 3-hour range, but mostly it was up here. And then there's even one where we went kind of crazy down here. I hope that you are starting to see and feel comfortable navigating around the wonderful world of NumPy. You'll see it everywhere, like everywhere. And being able to use it and understand the terminology surrounding it will greatly help your data journey. Matplotlib is just one of hundreds of data-related libraries that work great with NumPy. I am excited to see what you do with it.
You did it. You've got another course under your belt. Great job sticking with it. I hope that you're able to comfortably navigate the documentation as well as look back on the reflections that you made as you were picking up this versatile library. You'll see it popping up in just about every direction you look, so I'm glad you got a chance to get your feet wet with it. I also hope that you consider taking on the 100 Days of Code challenge. I find it really helps me to stay motivated and learning every single day. The community is wonderful and inspiring. Let me know if you do it. Speaking of community, don't forget that you can lean on the Treehouse community for just about anything. If you're wondering something, just drop your question in there. It doesn't have to be related to a course. Just reach out and you'll be greeted with a friendly response. It's kind of amazing. See if you can't help someone out with a question that they're having. Nothing helps knowledge stick more than crafting an answer. The cheat sheet that we built together in this course is available for you to download. I've added it to the teacher's notes. Your voice matters. Your feedback is greatly appreciated and we'd love to hear from you. Your comments, concerns, and ideas really do help shape the content that we build here, so please keep them coming. We want to know what you'd like to see more of, as well as where we can improve. So please keep us posted on what content you'd like to see, as well as what direction you're heading in your own personal data journey. I hope that you can now recognize the abbreviation when we do import NumPy as NP as both NumPy and no problem. This library is huge and can at times seem overwhelming. So again, excellent job completing this course. Nothing's stopping you now. You got this. No problem, right? There are always more courses coming your way. So until next time, see you real soon.